Welcome to the Creating Type Class and Instances lesson. We'll start by learning the concept of overloading. Then we'll learn how to create type classes and instances using the equality type class. We'll define the equality type class, then multiple instances, and then we will improve on the equality type class using mutual recursion and learn about minimal complete definition. Then, because there are a few edge cases that make us trouble, we will also implement other two type classes, the WeAccept type class and the container type class, to cover those cases. And finally, we will explore subclassing using the Ord Type Class. At the end of the lesson, we will learn about deriving and when should you derive or not your instances. Let's get started. Before learning what overloading is, let's learn what the word date means. What does date mean? If I would say that you have only one chance to answer, and I will give you $100 if you answer correctly, the intuitive answer is, it depends. If you're saying, what is your date of birth? Then it means the time at which an event occurs. If you're saying Joe took Laura on a date, then it means a social engagement that often has a romantic character unless Joe gets friend-zoned. If you're saying I want to date a fossil, I want to believe you're not referring to a romantic social engagement, but to the act of estimating or computing a date or chronology. And if you look up the word, date is also the name of a fruit and has even more definitions. In programming, we will say that the word date is overloaded because it has multiple definitions for the same name. The word overloading is overloaded itself. In everyday context, it usually means to put too large of a load into something. In regular programming context, it means having multiple implementations of a function with the same name, what we just saw. How this works in practice depends on the language. For example, some languages, like JavaScript, don't support overloading, so you cannot do it. And in others, like C++, you can create multiple functions with the same name, and the compiler will choose which definition to use based on the types of the arguments. In Haskell, overloading means having multiple implementations of a function or value with the same name. Of course, Haskell had to step up the game. In Haskell, overloading is not restricted to functions. Values can be overloaded too. For example, the literals 1, 2, etc. are overloaded because they could be interpreted as any numeric type, int, integer, float, etc. The value min bound that comes with the bounded type class is overloaded because, for example, when used as a character, it will have a value /null character. It's not an actual null, it's just a character with that content inside. While as int, min bound has the value -2, 1, 4, 7, etc. So the minimum value an int can have. The equality operator works with many types, each with its own implementation. And also the function max, for example, also works with many types, each with its own implementation. The first two examples are overloaded values, and the last two are overloaded functions. So, we've been using overloaded functions and values all along. The question is, how do we get those in the first place? Well, the mechanism that allows overloading in Haskell is type classes. In the Introduction to Type Classes lesson, we saw the utility of type classes. It basically boils down to having functions that can be used by many different types while having the safety that they only take the ones that they can work with. So, if you create a function that takes two numbers and add them together, that function works with all numeric types while also having the compiler stop you when you try to give it a non-numeric type. Type classes are a pretty unique feature. Not many programming languages have them. But the good thing is that they are surprisingly easy to use. When creating your own type class, you only need to do two things. Create a type class stating some behaviors, and make a type an instance of that type class with the implementation of those behaviors for that specific type. That's it. Practice makes perfect. So let's learn by doing. We will start by redefining the Eq Type Class. The Eq Type Class comes with Haskell, so you don't have to define it. But let's say that we live in a world where the Eq Type Class doesn't exist, and every type has its own function to check for equality. Because of that, you have to learn a bunch of different functions that all do the same, checking for equality. But, as Lennon said, imagine, while living in that horrible world, imagine all the types living in peace and using the same function. You may say I'm a dreamer, but let's do it anyway. We can define the Eq type class like this. In the first line, we start with the class keyword to indicate we're creating a type class, followed by how the type class will be called, EQ in this case. Then we write a type variable A that represents any type that will be made an instance of this type class in the future. So it's like a placeholder. And finally, we use the where keyword to start the block where we define the behaviors of a newly created type class. And now comes the cool part. We have to define the behaviors. To do that, we write the name and type of the functions or values we need. In this case, we define the behaviors to be the equals functions to check if two values are equal, and the not equal function to check if two values are different. We also indicate that both take two values of the type A we specified as the parameter of the type class and return a boolean. True if the condition passes, false if it doesn't. And done. We have our EQ type class ready to go. This means we have the name and types of the two functions that the EQ type class provides. We don't have the definitions here because each type will have its own definitions. And those definitions are provided when defining the instance for the type class. To define an instance for the EQ type class, first we need a type. So let's define one for the payment methods that a customer can use in our app. So we have the data type payment method that can be of value either cash or card or CC, standing for cryptocurrency. Then we create a type synonym user that contains the string that identifies our using in some way and the payment method that user uses. And if we want, for example, to check if two users have the same payment method, we could write a function like this one. But if we try to run this cell, we see that the compiler won't let us use this code. And it tells us why. It says no instance for the EQ payment method arising from a use of equals in the expression PM1 equals PM2. So we are using equals in the expression PM1 equals PM2, but because equals is a behavior of the EQ type class and our new payment method type is not an instance of the EQ type class, it doesn't have the implementations of equals and not equals to use. To fix this, we will make it an instance. To create an instance, we use the instance keyword followed by the name of the type class we want to make an instance for, the type that will be an instance of that type class, and the where keyword. Then, inside that block, we implement the functions defined in that type class. As you can see, because now we are creating an instance of a type, we replace the type variable a we had in the type class definition with our specific payment method type. And because we are creating an instance for the EQ type class, we need to implement the equals equals and not equals functions. So we will do just that. We are implementing both the equals equals and the not equals functions. For every possible pair of values, we are indicating the result of the function. So if the functions equals equals is applied to cash and cash, both are the same value, so we return true. Same with card, same with CC. Any other case, we don't care about the values because we know they will be different, so we return false. In the implementation for not equal, it's kind of the same. For every case when the values are the same, the not equal function has to return false because they are equal. So we define the functions when both values are the same as always being false, and any other value that will be different, so we return true. And that's it. That's how you define a type class and make a type an instance of it. Now, payment method can freely use the EQ behaviors. Let's see. If we run this cell, we see that we didn't run the previous cell. So let's run this cell. Now we have the instance. And if we run this cell, we see that our payment method type really has the behaviors of the EQ type class. And the previous function that didn't work before, now it does. Our work is technically done. We have our type class and our instance. But there's a property of the functions we just defined that we are not taking advantage of. If two values are equal, that means that they are not different. And if they are different, that means that they are not equal. So we know that for each pair of values, equals equals and not equals will always give us the opposite Boolean value. We are on our way to becoming epic Haskell developers, and epic Haskell developers can do better than that. So let's use this knowledge to improve our type class and instances, starting by redefining the EQ type class like this, which is how EQ is actually defined in Haskell. Let's analyze this code. Because both functions have the same type, we can specify them in a single line. And yes, we are also writing function definition in this type class. We can do that as long as they are type agnostic, because they have to work with all types. Looking at the definitions in more detail, we see that we are using the not function. The not function takes a Boolean and returns its opposite. So, in the third line, we are saying that applying not equals to x and y is the opposite of applying equals equals to the same values. And in the fourth line, we are saying that applying equals equals to x and y is the opposite of applying not equals to x and y. This is called mutual recursion, because both functions are defined in terms of each other. By defining equals equals and not equals as the opposite of each other, Haskell can infer the behavior of one from the other. And of course, like any other recursion, it needs a base case to know when to stop the recursion. And that's what we provide when implementing an instance. For example, let's redefine the payment method instance for this new type class. As you can see, the instance is the same as before, but now we only define one of the two functions. And that's it. Because now the compiler can infer the value of one function with the other, we don't need to implement both equals equals and not equals. We can implement the more convenient one and call it a day. This is called minimal complete definition, because it's the minimum you have to implement to get a fully functional instance. You can take advantage of this by checking the minimal complete definition of any type class using the info command. For example, if you run the info command for the Eq Type class, you will get this. In this line, it says that to have a minimal complete definition, you have to implement equals equals or not equals. You do not need both. You need one or the other. In the real world, almost all types are instances of the Eq Type class. But remember, we are in a parallel universe when you're a visionary creating the Eq Type class to make the world a better place. So if we stop here, the equals equals and not equals functions wouldn't be overloaded because they will have only one definition for the payment method type. But there's a reason you decided to create this Eq Type class. And the reason is that you thought that the behaviors it provides are useful for many types. For example, the blockchain type. We create a blockchain type that has three values: Cardano, Ethereum, and Bitcoin. Then we want to use the equals equals and not equals functions with it, so we create an instance of the Eq Type class for the blockchain type, where the equals equals function for applied to Cardano and Cardano are true, applied to Ethereum and Ethereum are true, applied to Bitcoin and Bitcoin are true, and any other combination of values is false. And that's it. We can run this cell, and as you can see, we can use both functions with our type. Now, the equals equals and not equals functions are truly overloaded because they have more than one definition depending on the type of values they are applied to. We did it, and we are on a roll, so let's keep going. So far, we created two instances of the Eq Type class, both instances for non-parameterized types. Let's learn how we can define an instance for a parameterized type. To create an instance for a parameterized type, first we need a parameterized type. The box type should do. Now we can create our instance, but we cannot do something like this. Why? Well, if we take a look at the Eq Type class using the info command, we get reminded that the type variable A is a concrete type. We can see this in two different places. If we check the type of the functions, we see that the type variable A is alone between the arrows, so it represents a concrete type by itself. And because of that, the kind of the Eq Type class clearly states that it takes a concrete type and produces a constraint. Type classes always have a kind that returns a constraint. Because type classes don't produce a type, they produce a constraint for polymorphic values. So if we see a kind that returns a constraint, we know it's a type class and it goes to the left of the fat arrow to constrain polymorphic types. On top of that, we don't need to check the functions to know how the type classes use the type variable A. The kind already tells us if it needs a concrete type or a specific type constructor. So, because of EQ of kind start to constrain, we know that the parameter A of EQA is a concrete type. But if we check the kind of box, we see it's not a concrete type, but a type constructor that takes one type as parameter and returns a concrete type. So what do? We could apply box to another type to get a concrete type, like this. That technically gives us the concrete type we need. So we could create instances like this. And it would work perfectly, but this is a lot of work, and we already went through this when defining functions and solved it with type variables. This time is no different. By defining this instance, all the types created using the box type constructor like box string, box int, etc. will be an instance of EQ. Now, wait a second. How do we define the instance if we don't know the type of the value inside the box? Well, if we decide that two boxes containing equal elements are equal, that two empty boxes are equal, and that everything else is different, we can define the behaviors like this. In the first formula, we define equals equals for the values of box A by applying equals equals to the values the boxes contain, because has X is of type box A, X is of type A. Same for the rest of values. So, if both boxes contain the same element, the boxes themselves are equal, else they are different. So, we are making the instance of box A depend on the instance of A. In the second formula, we specify that if both boxes are empty, they are indeed equal. And for every other case, the boxes are different. This makes sense, but there's a huge oversight in our part. Did you spot it? It's okay if you didn't. That's what the compiler is here for. If we run the cell, we will get a compiler error. It says that no instance for EQA arising for the usage of equals equals. Okay, so the compiler is telling us that we are applying the equals equals functions to a type that doesn't have an instance of equals equals. Where are we doing that? In the expression x equals y, here, inside the equation has x equals whatever, in the instance EQ box A. And the compiler is correct. We are using equals equals between x and y of type A without making sure that the A type itself is an instance of EQ. So what should we do? Well, the compiler also told us how to fix this. A possible fix is to add EQA to the context of the instance declaration. Same as with functions, we can add the constraint that the type A in the instance of EQ box A has to also be an instance of EQ Type Class. We can do this like that. The only thing we need to do is to add the constraint that the type A inside box A has to also be an instance of the EQ Type Class. This way, the type box A will be an instance of EQ for all types A that are also an instance of EQ. You can see that if we run the cell, the compiler won't complain anymore. And we are done. We can use this new instance like this. If we run this cell, we'll get a few different results. We will see that these three values, of course, gives us the expected result. And in the last value, the compiler complains that there's no instance for EQ choice, which is correct because we just created this type and we didn't create an EQ instance on purpose, to show that even when wrapping the type inside another type, the compiler will still protect us from our human mistakes. Okay, now that we did everything step by step with the EQ Type class, let's do everything again, but quicker and with a new type class that is not part of the standard Haskell, the WeAccept type class. Imagine we are writing an app that accepts payments for a company, and this company doesn't accept all payment methods, all blockchains, and all countries. So you have to create functions to check that. We have to create the WeAccept payment function that takes a payment method and returns a boolean. Then we have to return a different value for each case of P. When the case of payment method is cash, we don't accept it. If it's card, we accept it. If it's cryptocurrency, we do accept it. Then we have to create the WeAccept blockchain function that takes a blockchain and returns a boolean. And this time we have the cases of blockchain when it's Bitcoin. If it's Bitcoin, we return true. If it's Ethereum, we return false. If it's Cardano, we return true. And finally, we have to create the new type country that has a single field called country name that is of type string. And we have to create the WeAccept country function that takes a country and returns a boolean. And in this case, we take the country and create a case statement that says, okay, when the country name of country is Mordor, we don't accept them. And every other country we do. Seeing this code, we realize that this behavior of checking if the company accepts something could be used in many other aspects, like providers, technologies, etc. There are a lot of things that a company could decide to accept or not. To avoid having a bunch of different functions that do the same thing all over your code, we decide to create a type class that represents this behavior. And that type class looks like this. We create the WeAccept type class that takes a single type parameter where we provide the WeAccept function that takes that type and returns a boolean. And if we check the kind of our newly created type class, we see that WeAccept takes a concrete type and returns a constraint. Now that we have our type class, we can create the instances for payment method, blockchain, country, and even box, like this. We create an instance of WeAccept for payment method where we accept the value of payment method for each case is the same as before. We create another instance for blockchain where WeAccept is the same cases as before. An instance of country where WeAccept is the same cases as before. And finally, we create an instance of WeAccept for box A, where WeAccept of the box when the box has something is the same as WeAccept applying to that something inside. So we accept the box when we accept the value inside the box. And if WeAccept is empty, we return false. Because we are applying WeAccept to X of type A, the value inside box has to also be an instance of WeAccept. That's why we have this constraint. And done. This gives us the ability to apply the overloaded WeAccept function to 4 different types. And we can also create functions that can be applied to all the types there are instances of WeAccept, like this. In this case, we create the function that takes a type and returns a string when this type has to be an instance of WeAccept. And in the definition of the function, we take the input and we apply WeAccept to the input, and it either returns true or false. So if it returns true, we can do something fancy, else we just don't. If we run this, everything works perfectly. So this fancy function will work with all the types that are instances of WeAccept. Another type class under our belt. It's getting easier by the minutes. We'll do one more example before continuing to the next section. This one is a bit more difficult, but if you understand it, you will be able to understand almost any type class. Let's start. This is the scenario. We are working on a logistics software that has two different types of packages. A regular box that may or may not contain something, and a present that may or may not contain something, but that it always has a name tag for who's the present for. So we have these two types. The box type that takes one type parameter and has the empty constructor and the has something constructor. The present type that takes two parameters, the tag and the contents, and it can return either an empty present that still has a tag or the present that has a tag and contains something. So we have two types and each type has two different constructors. As you can see, the kind of box tells us that box takes one type, the type A, and returns a concrete type. And the kind of present tells us that present takes two types, these two types, to produce a concrete type. Because we decided that the tag of the present can be a number, a name, or anything else that could identify a customer, we also parameterize this type. Now, we have these two types, and a few parts of the process require functions that are common to both types. We need a function to check if a box or a present is empty. We need one to check if a specific value is contained inside a box or a present. And we also need one to replace the contents of the box or present. Instead of writing the functions by themselves and then transforming them to a type class and instances like we did in the two previous examples, we go straight to type classes. This is our type class. The type class will be called container because it provides behaviors related to containers. The type variable is called C because it's a container. Now, let's write down the type signatures. We will start with the replace function. So why not? The replace function takes two inputs. A container that has some value of type, let's say, A, and another value that can be of the same or different type than the one inside the container. Let's call it B. The function replaces the value of type A inside the container with the one of type B. So, in the end, we get a value of type container B, because the value it contains is now of type B. And that's it. Now, let's do the contains function. Contains takes two inputs, a container with a value of type A inside, and another value that will be compared to the one inside the container. So it needs to be a value of the same type that the one in the container, A. And we will also need A to be an instance of the equality type class because we will use the equals functions to check if those two values are the same. The function takes a value, check if it's the same as the one inside the container, and returns either true or false, so it will return a boolean. We're good so far. Now let's do the final function, the isEmpty function. This function takes just one input, a container that contains a value of type A, And the function takes the container and returns either true if it contains a value and false if it doesn't. So it returns a boolean. And that's it. Our type class is ready to go. And because each arrow separates a value and all values need to have a concrete type, we know that both A and B are concrete types by themselves because they are alone between arrows. Using the same reasoning, we know that CA and CB have to be concrete types. And because A and B are concrete types, this means that C is a type constructor that takes a concrete type and returns a concrete type. We can see this if we check the kind of our type class. As you can see, the kind of container tells us that C is a type constructor that takes a concrete type and returns a concrete type. And the container type class takes this C and returns a constraint. Now that we have our type class, let's create the instance for the box type. Here we have our type class as reference and the implemented instance. Notice that we create an instance for box, not box A. For the equality type class, we applied box to the type variable A to obtain the concrete type box A, because the Eq type class needed a concrete type as parameter. But container takes a constructor of kind star to star, which is the same kind as box. So we have to pass box without applying it to anything. The actual implementation of the function is pretty straightforward. Because box has two value constructors, we will usually have two formulas per function. So to implement the isEmpty function, we have to take into account the case when the box is empty, and in that case we return true. And if the box has something, we don't really care what it has. We just return false because it's not empty. Now, to implement the contains function, we first pattern match for a box that has some value, and we bind it to the variable x, and compare this value to the second input of the function using the equals function. That's why when we use the contains function, the type A has to be an instance of EQA, because we are using the equals functions to compare them. Now, if the box is empty, we have nothing to be compared to the value, so we just ignore the value and return false, because if the box is empty, obviously it doesn't have the value that we want to check for. Finally, we have to implement the replace function. The replace function takes two parameters, a container of type A and a value of type B. Interestingly enough, the replace function doesn't need two different formulas, just one will do, because for both cases when the box is empty and the box has something, we will return the constructor has with a value inside that's the one that we pass as the second parameter. So we can safely ignore the whole box. Now let's create the instance for the present type. Let's do this a bit smaller. Okay. The instance is for the present t type constructor. This is because present by itself has a kind of start to start to start, meaning it takes two concrete types to return a concrete type. But because container takes a type constructor of kind start to start, we have to apply present to a type, like for example present string or whatever, to obtain the kind that we need. And because we want to be able to use any type as a tag, we use the type variable t. Okay, so same as before, the actual implementation of the functions are straightforward. The isEmpty function, in the case that the present is actually empty, we ignore the tag and just return true. Yeah, it's empty. In any other case, it's false because it has something. We don't care what it has, but it has something. Then, to implement the contains function, in the case that the present contains something, we take that something and the second parameter and compare them to see if they are equal. That's why, again, we need A to be an instance of EQA. If, in the case that the contains function takes an empty present, we ignore the tag, we ignore the second parameter, and just return false, because it's empty, so it won't contain whatever we want to check for. And finally, the replace function. If the present has something, we pattern match for the tag, bind the tag to a variable tag, and take the second parameter and create a new present for the same person but with the new value. And now we do need a second formula. That's because in the case that the present is empty, we can't create a new present that has something without the tag value. So we need to pattern match for the tag of the empty present and then create a new present that has something with the same tag and the new value. To reap the rewards of our work, here are a few examples using our new type class behavior. And again, it's too big. So we can check if the box has false, contains false, and we get that true, yeah, it does. We can also check if the box has A, is empty or not, because if it has something, it returns false. Then we can check if the present for Tommy that contains 5, and we get that, yes, true, it contains 5. And finally, we can also take the present for Tommy that has 5 and replace the contents with a string of value Arduino. And we get back present for Tommy is an Arduino. We can also create functions like the guess what's inside function that takes a container that has a value of type B inside. In this case, the container is of type A, but we could have written C and C here, and it's the same. And also takes a value of type B and returns a string. So what does guess what inside function do? It takes the container and the value and checks if this container contains this value, then return you are right, else wrong. And now, because this type constructor C is a polymorphic type that has to be an instance of container, we can use this guess what's inside function with both boxes and present. So we can apply guess what inside for present for Mary, a Raspberry Pi, and the guess of Mary, a pony, and we get that it's wrong. We can also guess what's inside a box that has 1. We say 15, it's also wrong. Now, I know this might be a bit overwhelming. Understanding this type class and instances was the trickiest part of the whole lesson. It might take a while to fully grasp what we just saw. But don't worry, if something doesn't click, it will with some practice. That's why it's important to do the homework. Also, it's okay if you need to rewatch the video a few times. Now, let's learn about subclassing. After everything we went through, this is a piece of cake. We never talked about subclassing before, but you already know how it works. Let's see it in practice while defining an instance for the Ord Type Class. If we run the info command on the Ord Type Class, the :i ord in GHCI, we will get something like this. Everything checks out, except for that EQA. We have seen this in both functions and instances, but never on type class definitions. This EQA means what you imagined. To make a type A an instance of Ord, first we have to make it an instance of EQ, meaning that EQ is a prerequisite for Ord. In other words, EQ is a superclass of Ord, or Ord is a subclass of EQ. Superclasses allow simpler signatures to be inferred. By saying that a type is an instance of Ord, not only do we know that it has the behaviors of Ord, but also the behaviors of EQ. On top of that, this allows us to have the behaviors of EQ type classes to define the instances of the Ord type class, which is actually something that happens in this case. The Ord type class uses functions provided by the EQ type class. Even though we can't see them, we know that there are a bunch of function definitions defined in terms of each other. That's why we can implement the entire instance by only defining compare or less than equal. The info command doesn't show all the code because we, the developers, don't care about it. We only want to know which behaviors come with this type class to see if it's what we need. The kind of the type class and minimum behaviors we need to implement to only implement those. If it depends on another type class, to implement that one before this one. And finally, which types are already an instance of this type class. We don't show this here because it's a huge list, but right below this, we have a list of all the types that are instances of this type class. This helps us because we can see which types can already use those behaviors. We need to know all that, and that's exactly what the info command shows us. So, to make a type an instance of Ord, first we have to make it an instance of EQ. Luckily, we already created a few instances for EQ before, so we are already halfway through if we want to create the Ord instances for any of those types. For example, if we want to create an instance of box A for the Ord type class, we have to implement one of the functions needed from the minimal complete definition. In this case, we choose the compare function and we write it like this. We create the instance of the Ord for box applied to the type variable A because we need a concrete type when A is also an instance of Ord A. This is because we are using compare here to compare the contents of the two boxes. So, what's happening here? If both boxes have values inside, we compare the values. If one of the boxes is empty and the other isn't, it doesn't matter what's inside the one that has something. It will always be greater than the empty one, because I say so. You could implement it differently. I choose to say, okay, if the box is empty, I don't care what the other one has, empty is less than the box that has something. And if the first one has something, it will be greater than the box that it's empty. And finally, if both are empty, they are equal. You can see that here we are testing our implementation. We can use greater or equal than. We can use all the behaviors of the Ord type class, so we can check if the box has 9 is greater or equal than the box that has 5, and we see that yes, it's true. If we compare empty to has 0, we can see that empty is lesser than has 0. And we can say if empty is less than empty, we say, of course, this is false because they are equal. And boom, that's it. We have our instance of the Ord type class. So, as a recap, we created the EQ type class with 3 different instances, the WeAccept type class with 4 different instances, then the container type class with 3 instances, and finally, we made a type an instance of the Ord type class. Congratulations, you know everything needed to work with type classes. We do have one final section though. As the final section of the lesson, we will learn how and when to automatically derive instances, saving us some precious time and reducing the amount of code we have to maintain. Derived instances are an automatic way of making a type an instance of a type class. This is possible because many common type classes are usually implemented the same way, and some clever guys with PhD figure out how to generate this code based on the type's definition. This is limited to EQ, Ord, enum, show, and other type classes defined in either the prelude or the standard library. Those are libraries that come with Haskell and that we'll explore in future lessons. For now, think that all the type classes we used until now and that we didn't create ourselves can be derived. To use this feature, add the deriving keyword at the end of the type declaration with the names of all the type classes you want to derive. For example, if we do this, we are creating the data type choice of values no, I don't know, or yes. And we are deriving the instances for EQ, Ord, show, bounded, and enum. And as you can see, we can use the behaviors of all those type classes. We can compare for difference a behavior of the EQ type class. We can check if one is greater than the other, a behavior from the Ord class. We can transform the yes value to a string, a value that comes with the show type class. We can check the minimum value of the type class. We can see that no is the minimum value. This is a behavior of the bounded type class. And we can also calculate the successor of no, which is I don't know, because it's the one that comes after no. This is a behavior from the enum type class. And there you go. Your choice type has all the behaviors provided by all those type classes. If we could do that from the start, why in the world would you care for manually deriving instances? Well, one of the reasons is that not all type classes can be derived. And the other is that deriving can sometimes go wrong. Let's make this a bit bigger. Each type class has its own set of rules for deriving instances. For example, when deriving the Ord type class, value constructors defined earlier are smaller. So, in this case, we define the payment method that can have three different values, cash, card, of CC. So we define cash before card and card before CC. So cash is smaller than card, which is smaller than CC. And in this case, if a value constructor has a parameter, for example, has A, and two values are made from the same constructor, here and here, the parameters are compared, like we did when defining the instances ourselves. Those are rules that the compiler follows to automatically create the Ord instances for your type. Other type classes have other rules. We won't go over the rules of each type class, but I will provide a link with a short explanation in the interactive lesson, in case you want to learn more. Now, let's say we want to use a type to manage lengths in a civil engineering software. We work with both meters and kilometers, but because we don't want to accidentally mix those and get a potentially catastrophic error, we define a data type with two constructors, one for meters and one for kilometers. Both contain a value of type double. And we will also derive the EQ. As you can see, we created a data type length that has two values, m that represents meters and contains a double, and km that represents kilometers that contains a double. And we derive the EQ instance automatically. But as soon as we start using this data type, we find a little problem. We know that 1,000 meters equals 1 kilometer. But when we test this in our code, we get that it isn't. That's because when we derive EQ, the compiler generated this code. In the case that both constructors are meters, we pattern match and bind the values contained inside the constructors and check those for equality. And in the case that both are kilometers, we pattern match for the value contained inside and check if those are equals. Any other case, meaning if the constructors are different, we return false. This works great if we are comparing meters to meters and kilometers to kilometers. But we have the wrong implementation to compare between constructors because Haskell doesn't know that the values of different constructors relate in any way. Haskell just assumed that if the constructors are different, their values are too. So in this case, we have to write the instance ourselves to take into account the relationship between the constructors. And we can write this instance like this. Our data type length of values m and kilometers. This first part is the same as before, but in the case that they are different, if the first is meter and the second is kilometer, we take the value in meters and check if that is equal to the value in kilometers multiplied by 1,000. And in the case that the first one is kilometers and the second one is meters, we take the first one in kilometers multiplied by 1,000 and check if that is equal to the value in meters. So now these two values that in theory are the same are also the same in practice. That's why it's a good idea to be conscious of how each type class is derived, to know when you can derive them and when you have to write the instance by hand. And to finish the lesson, here are a few tips for real-world coding. First, everything I explained today applies to all type classes. Also, we don't define type classes that often. Usually, the ones that come with Haskell are all we need. But we do implement instances quite a lot, and it's usually a good idea to derive them. If you're in doubt, try automatic deriving and check your assumptions. You can always come back and manually define their instances. And finally, let's make this a bit smaller. You can pick a type class definition using the :I command on GHCI to see the minimum behaviors to implement when creating your instance. Just implement those and you're done. And that's it for today. Make sure to complete the homework and I will see you in the next one.